Calculus 1 curriculum lesson plan. This calculus curriculum has been designed to promote a student-centered approach that fosters deep understanding and practical skills through active learning, collaboration, and real-world applications. It aims to engage students in meaningful learning experiences that connect academic content with real-world situations, preparing them for future challenges and opportunities. The prerequisite for this class is a solid foundation in algebra, geometry, trigonometry, and pre-calculus concepts. The curriculum emphasizes conceptual understanding over rote memorization as is divided into the core units of limits, derivatives, applications of derivatives, integrals, and the application of integrals. The curriculum uses various technology to help students visualize the content within calculus. Besides graphing calculators, free online resources will be utilized, including GeoGebra, Desmos, and MyOpenMath. Students will develop essential teamwork and communication skills through active learning and collaborative activities. Assessments will include both formative and summative. A variety of formative will be used to check students' understanding. Summative will include unit exams that will consist of computational and application problems. Students will also complete projects to foster development of their critical thinking and problem-solving skills. This class is intended to facilitate an appreciation and love for mathematics, along with a connection to daily life.
Unit 1, limits. Here are my top 10 teaching practices as I will be implementing them into my lessons. Starting off with the objectives. At the end of the week-long lecture and activities, the students are expected to complete the following objectives and understand that limits are the foundation of calculus. So I have all those listed, and I will be listing them in each of the lessons as well. Lesson 1, Introduction to Limits. The objectives that we have here are students will understand what a limit is and identify limits on graphs. Second one, students will understand how to write a limit. First thing I'm going to start with is a bell ringer. Students will think of real life scenarios where limits are used, and students will use 5 different functions. Basically, those 5 different functions, I want 5 different functions with different characteristics. So I might throw up a piecewise function, might throw up a scatter plot, might throw up a quadratic, cubic, square root, something with 5 different characteristics. Okay, down below we'll look at these functions from the bell ringer and solve limits at various x values. Okay, I want to explore constant limits, one-sided and two-sided limits, and infinite limits with the students. I plan on using the I do, we do, you do strategy for this. Okay. Students will have done an exit strategy and should have homework to go over in class to check on accuracy. So basically, I'll give an extra strategy to determine if my students understand what we're doing or what tomorrow's lessons needs to be. I will give homework, give them 10 problems. Hey, here's a couple functions that are already drawn out. Find the limits on each of them. Lesson 2, continuation of infinite limits and limit laws. I chose to do a continuation of infinite limits primarily to see if we need to recover anything or clear things up, or if we didn't even get to all of it. So starting off with our lesson objective, students will recognize basic limit laws. Students will use the limit laws to evaluate a limit of a function. Students will evaluate a limit of a function by factoring. Students will use the limit laws to evaluate a limit of a polynomial or rational function. Students will evaluate a limit of a function by factoring or by using conjugates. So the first thing that I'll start us off with, again, was a bell ringer. And as you can see, if they're in there, there will be problems involving factoring and conjugates. We haven't covered those since pre-calc, so I'll want to refresh them on those. especially factoring when a is greater than 1. Going over this, we're going to again work with the I do, we do, you do, and I hope that they will be following along. And the students can use partners during our lesson. I want them to be referencing each other and asking each other questions, and there's going to be times that I'll be walking around, especially with the you do part. Our homework that we'll have here, again, we're going to have an exit strategy, but then we'll have homework to each of the limit laws and the techniques. Probably looking at about 12 problems. Lesson 3, applying the squeeze theorem and trig limits. Our objectives for this lesson are students can evaluate the limit of a function by using the squeeze theorem, and students can evaluate the trig limits. Again, we'll start the lesson off with a bell ringer, going over yesterday's material. One thing that with this is I will be using GeoGebra to help demonstrate the squeeze theorem. And another thing here that I posted, as you can see, is I'll post a YouTube video on the Google Classroom for students as an extra reference. And I found that that was useful when I taught this last semester. I will prove to the students the special trig limits and apply those to the examples. Okay, the students will be taking notes and following examples. The students will be participating in class examples. My outcome, a worksheet with a few problems that the students can apply the squeeze theorem. Squeeze theorem is not something that's too crazy, so maybe keep it down to 2 or 3 problems. Lesson 4, review of limits. My main objective is to provide students with review problems to clear up any uncertainty regarding limits. Basically, what we'll do is we'll go over the squeeze theorem problems from yesterday, and then continue on with our review. I found that repetition works best when reviewing. So basically, my goal is to provide the students with different problems regarding the last 3 lessons in class. I want the students to be working together. I want the students to be working on this in their notes so they have this as reference and they can study on this later on. Preferably the next day we'll be taking an assessment that will determine if they met all of the objectives.
My name is Kaitlyn Larson, and I completed Unit 2 of Derivatives in our curriculum plan. So starting out, my unit has 7 lessons in it. The first one is Introduction to Derivatives. This lesson is all about learning what the definition of a derivative is, how they are applied, and what the relationship is between the original function and the derivative, and it also teaches students the notation. Lesson 2 is differentiability. This is where you identify where derivatives don't exist and applying the intermediate value theorem. 3 is differentiation rules. These are going to be your basic derivative rules. For example, product rule, power rule, quotient rule, among other rules as well. This is a larger lesson and probably will take quite a few more days than the other ones, just because there are so many rules packed into this lesson and they are very important to know going forward. Lesson 4 is trigonometric functions and their derivatives. This is where the kids are going to learn about the derivatives of trig functions. They'll also be graphing the trig functions and their derivatives to kind of identify the relationships between the two. Lesson 5 is chain rule. 6 is implicit differentiation. And then 7, the last one, would be exponential and logarithmic functions and their derivatives. So getting into the actual lesson plan, I won't go through all of it, but the basic outline for each lesson is using the I do, we do, you do method and explicit instruction. Since this is such an information-dense unit, and it has information that kids do need going forward before they complete all the other units that we do, for example, applications and integrals, they do need to completely understand how to perform each one of these operations. So explicit instruction is key here to help students with that. In this, there is a lot of group work. There is a lot of using graphing calculators. I also have the students rate their understanding on a scale of 1 to 4 in most lessons. I would recommend doing this in all of the lessons. This gives you, the teacher, a really good understanding of where the kids are at, and it also tells the kids, like, okay, I actually know what I'm doing, or maybe they know that they need more help. I also recommend letting them do independent practice at the end of these, just so then when we do applications of derivatives, they know what they're doing, they feel confident in what they're doing, and they've had that practice. Throughout the lessons, there are little mini quizzes, a lot of exit and entrance tickets, and reminders of the things that they learned in the previous lesson. A couple of things that I put in this unit are 2 cumulative practice days. So this is a day where students are going to review everything they've learned so far in this unit and the previous unit, which was on limits. This is just helping kids cement that knowledge in their brain and reviewing any information that we've already learned. This is going to help as they prepare for, say, the final test or the AP exam. And there are several options that I listed here that teachers could use depending on what would work in their classroom. So the first one is just a cumulative practice worksheet, and the second one is friendly competition, just to jazz it up and maybe add some fun to your classroom. As we go down, again, here's another cumulative practice day. I highly recommend that you add these throughout your curriculum just so kids keep that refresher in their mind. And then lastly, moving on down to assessment. So there are 2 parts to the assessment. The first part is a project that they're going to do. This isn't necessarily an application project, it's more of a fun project to help them really cement those rules into place. So this project is all about creating a board game. It can be any board game they want based on one that is already created, like Monopoly, or if they want to completely make up a new one, that's totally fine. They have to make up the rules and the physical board game. And the tasks for the board game will be finding derivatives using the rules that we've learned from each lesson. Teachers can modify the rubric that will be provided to fit their classroom needs. They can also modify the amount of time allowed to fit their classroom needs. And this will serve as kind of your study guide, if you will, or your review. Of course, if you wish, you can always add a study guide before you take the final exam after this project, but this could be a really fun and engaging way for students to show you and practice what they've learned. And it's also advised, this last sentence here, to take a day and have students play the other games that their classmates created. This is just a fun day where you get math practice in and you also get to have some fun. And then at the very end of the whole unit, the kids are going to take a unit exam. This is to test for recall and comprehension of the entire unit. And this is just so that we know that they know what they need to know before going into Unit 3, applications of derivatives.
This is Unit 3, applications of derivatives. The things that are very important to me in this unit are active learning, so a lot of class discussion you will see, project-based learning, I use those in my summative assessments, applications, that's the entire unit is applications, and then again the use of technology. Students in my classes and in this unit will be using graphing calculators all of the time, every day. We also work on Desmos and MyOpenMath sometimes. So first unit, you can see, starts out with class discussion, and we have some group work where they're completing an assignment, so I know that they've understood what we talked about in our discussion. Lesson number 2 with derivatives and motion problems, I use think, pair, share, because students often already know something about motion, acceleration, velocity, all of those types of things. So I do this think, pair, share, and always using the student responses to guide that lesson. It becomes kind of Socratic seminar-esque, and some students know a lot of information if they're in a physics class, some do not because they haven't had anything since physical science. So they really do start to teach each other, and it is very fun to watch and be a spectator as those students help each other out with that collaborative learning. Obviously, we're going to do a lot of application problems at the end as their homework, and I do encourage them to collaborate and work together on all homework assignments, so that you will see throughout this unit as well. Lesson number 3, related rates, brings in lots of real-world scenarios. Review implicit differentiation is pretty much all I do as a teacher-led thing, and then I just do some examples on the board. I give students kind of the 5 steps that I want to see when they do these problems, but I throw an example up on the board and we start working together as a class. This is called Related Rates and AP Calculus Party because it's one of my favorite lessons to teach. But I allow the students to kind of guide each of the problems, and if we go down a wrong path, we go down a wrong path, and we talk about where we went wrong, what we could have done better, all of those types of things. So these are the specific examples that I use. The last one there is a very challenging one. It should probably be covered on a day 2, maybe even day 3 of related rates, depending on the amount of time you have in your class. After we do some examples together, I do give them this round table activity where students are split into groups of 5 and each person does one step of 5 different problems. So they get their paper, they do step number 1, they pass it on to the next person, they check their work, they do step number 2 and pass it until everybody has done all of the problems. There's a lot of collaboration in there. They discuss mistakes and challenges and all of those types of things while they're working on these problems. So a lot of collaboration in that one. Lesson 4, tangent lines and local linearity. It's kind of just a quick, easy lesson for students to do. So we just briefly review point, slope, form of a line, remind ourselves that a derivative is a slope, we find points, and we just find some tangent lines. Really easy, exit ticket at the end. Mean value theorem is another really fun exploration activity that I do with the students. They are given a worksheet, they work together in pairs, and they draw secant lines between 2 points on the graph and then try to find a tangent line that's parallel. And then there's questions after they do enough drawings where it asks them, where were you able to draw the tangent, where were you not, what kind of conditions were there, and it kind of leads them to what the MVT says. So the conditions for applying the MVT, and then also what the MVT actually says, where the average rate of change is equal to the instantaneous rate of change. So after the exploration, I bring the class together and we debrief just to make sure everybody's on the same and correct page. So they're working in partners on this one. They are kind of struggling through their own knowledge and forming those thoughts in their heads. And then they do their homework with a partner or a small group. Extrema and critical points. Again, you see here class discussion. Just asking them what they know about these certain vocabulary terms, introduce the new ones as they come up. Global versus local extrema is one that most of them have not heard about, but they do know what minimum and maximum are. And then we talk about how that relates to calculus and how we can use calculus to find them. Again, another discussion-based class. Intervals of increasing and decreasing. Start out with functions on the board, ask them about where it's increasing, decreasing, and then I just ask, how does this relate to calculus and the things that we've been talking about? They understand that is derivatives, so then they start talking about, well, what's the derivative in this chunk where it's increasing and decreasing? So they're really talking it through with each other and with me, and we come to understand where increasing and decreasing and how that relates to the first derivative. And then we also talk about the first derivative test to find extremes. And they're working together. Again, lesson 8, concavity and second derivative test. I kind of approach it in the same way, but this discussion does require typically more teacher guidance because it just isn't as obvious with that second derivative. So when we're looking at concave up like a cup, or concave down like a frown, it's not as intuitive that the second derivative relates to that, so I have to guide that just a little bit more, but students do come up with that stuff on their own. Lesson 9, we sketch functions and their derivatives. They know all of the information before. I use this table that you see in the middle of the screen to kind of just summarize everything and put it in a nice, neat little package. And I just give them prompts and attributes of f, f prime, and f double prime, and have them sketch what f might actually look like. We get a lot of different answers, and students will obviously look at each other's and be like, well, what is his right? Is mine right? Who's right? Who's wrong? And I don't tell them that. I just ask them if, as long as your graph has all of those attributes that you were given, then it's correct. So we put a bunch of them up on the board and talk about what makes them correct, or what mistakes might be included, and then we fix errors as necessary and move on. To wrap up that lesson, students do complete the functions and their derivatives activity on Desmos, where I can just see that they are making sure, or I can make sure that they are making the correct connections. Lesson number 10, optimization, more group work and real world problems in any sort of context, business, population, medicine, anything. And then we talk about how those derivatives should be interpreted in the real world. And that kind of tends to be the more difficult part, just because we haven't done that up to this point. So they talk about what that means. And then implicit relations in lesson 11. Students, again, already know how to do all of this information. So a brief review on implicit differentiation, and then we'll just do some examples together. Again, student-led, and if we go down a longer path or an incorrect path, I let it happen, and we go from there. Assessments, the formative assessments are so important every day. The daily class participation, in-class activities, worksheets, assignments, quizzes, all of those things are used often. Summative assessments, after lesson 4, I'm going to work on this roller coaster project for this coming year, see how it goes. I've never done it before. I'm going to modify this link here, and then a group project after lessons 5 through 10 for real world applications, where they're going to research and find a function and all of those types of things, and then interpret it, and we will present to the class just so we can see, again, more of that real world example stuff, and I don't have to go through all of the work of researching them. And then, of course, at the end, a unit exam where we both include computational and application problems, and we'll give students a chance for corrections to show some mastery if they didn't get it the first time.
Integrals. The objectives of this unit are for students to be able to approximate and actually find the area underneath the curve using rectangles, trapezoids, and also Riemann sums, and then integration rules, which will then build us into the fundamental theorem of calculus. The first lesson is on area underneath the curve with approximations. In this lesson, students will be approximating the area with left, right, midpoint, trapezoids, all those different things. They will be asked to discover kind of by themselves, like with the exhaustion method, how can we find the area underneath this curve? They can compare, contrast with the people around them of, I did this type of shape, you did that type of shape, how are approximations the same or different? And then at the end of that lesson, they have an option to do a little extension project where you give them a curve and a certain amount of approximations to find, and then either by hand or with technology with Desmos, they make a poster or some sort of presentation where they rank them from best to worst, where they have to justify with, well, this approximation seems like a better one than this one based on however they see it. So you can kind of get an insight into how they're thinking. Lesson 2, we are still finding approximations. The difference here is we're going to be a little bit more generic. So instead of saying we have 4 rectangles, we're just going to have n amount of rectangles, and we're going to create this nice Riemann sum with sigma notation formula that can be plugged into at the end, so that if you want to find 5 different approximations of the same bounded area, you can just plug it in at the end. This lesson is a good algebra review of plugging into function notation as well as using sigma notation. At the end of it, they will do an exit slip where the last question is going to be, how can this approximation change into an exact value? And that's a powerful question because most of the class is going to have a light bulb go off and say, I add in enough rectangles where it's the limit of that as it approaches infinity. So that question is how we end lesson 2, but it's really the beginning of lesson 3 of showing students the tie-in of, if I take the limit of this, if I add in enough rectangles, it's eventually going to fill the entire area because the rectangles are going to get so small that there's no overhang, there's no under or over approximation. It's just going to be the true limit. In lesson 4, we are still finding that area, or talking about the area underneath the curve, but instead of writing out the limit of the Riemann sum anymore, we introduce a definite integral from a to b f of x dx, and just start to talk about how these notationally look very different, but they mean the same thing. So teaching them, how do you recognize what is your function, what are your bounds, picture-wise, draw this, show what this means, what area are we actually finding, as well as going through those definite integral properties and tying them into what segment addition properties they learned in geometry. Again, this lesson very picture-based. They can draw pictures for everything, work with a partner, and kind of see like, oh, it makes sense why, if symmetry, how that comes into play and how that will affect our answers. Lessons 5, 6, and 7 are the indefinite integral rules. So finding the integrals with power and trig, and then moving into U substitution where they kind of monkey around with it and you put them in groups and encourage them to, okay, check your answer by finding the derivative. Are there other workarounds where you can multiply this all out and still find the integral? Or like the cosine of 9x, if you were to take the derivative to check it, it's not going to be right. So how can you change what your integral answer is to make that happen so that they can kind of discover that rule on their own? The last lesson for integral rules is just kind of the long division, the others, inverse trig, and within lesson 7, just making sure all the other ones are also being reviewed and getting them to understand that look for the ones that make sense first. Look for your U subs, look for the nice ones, and then these other ones might fit in there. For lessons 5, 6, and 7, because they are integration rules at the end of each lesson, they will be taking a quiz. If they earn less than an 85%, they will practice and retake it because it's hard to do applications of integrals if you can't integrate. So we need to make sure that they are comfortable with these rules. The last lesson is the fundamental theorem of calculus. So here we started this unit with area underneath the curve. We're ending it with area underneath the curve. So looking at how can we geometrically find the area underneath 2x from 0 to 5, and how does that tie into, if I take the antiderivative of 2x, how can we mess around with this? How do these two play together? And putting them in a group and kind of just encouraging them to plug in numbers, see what does that 0 and 5 really mean, so that they can essentially discover that fundamental theorem of calculus on their own. The assessment for this unit, since it is so skill-based, will look pretty traditional. There'll be a lot of questions of asking them to justify their answer with pictures and making sure that they understand a Riemann sum and an integral. Will they look like they are two very different things? That fundamental theorem of calculus really ties them together, and that's what we want them to do, is to understand how everything in this unit plays together and essentially has the same goal at the end of how do we find this area underneath the curve with the fundamental theorem.
Hello, this is Unit 5, Applications of Integrals, and this is Harmony Richman. This unit is all about taking the powerful tool of integration that we learned in the previous unit with learning techniques for integration and applying it to solve real-world problems. We'll see how integrals can be used to find areas, volumes, work done by forces, and even analyze shapes. Understanding these applications not only solidifies a student's grasp of integrals, but also showcases the practical utility of calculus in everyday life. For instance, imagine you're a civil engineer designing a new highway. Using integrals, you can calculate the exact amount of material needed to create an optimal road surface. Integrals can help you determine the optimal depth of a swimming pool or the most efficient design for a storage tank. In economics, integrals can be used to calculate consumer surplus, which tells you how much extra value customers receive by buying a good or service at a certain price point. The possibilities are truly endless. We've learned that calculus is all about understanding change. Derivatives help us find the rate of change in things, and integrals will help us find the total accumulation of change over a period of time. This unit will show students how useful integrals can be in various fields, ensuring students are more well-rounded mathematicians and problem solvers. By connecting these mathematical concepts to real-world scenarios, students will appreciate the relevance of calculus in both academic and professional contexts. Understanding integrals builds upon the foundation of the derivatives that we've learned about in previous units. The derivatives have helped us find the instantaneous rate of change, whereas integrals take a step further, allowing us to calculate the total accumulation of change over a period of time. With respect to the positive learning environment, this classroom is a safe place for exploration and learning. Students shouldn't be afraid to ask questions, make mistakes, and work together with their classmates. We're all here to support each other and deepen our understanding of calculus. This creates a positive learning environment, which is crucial for fostering curiosity, confidence, and collaboration among students. You will see in this particular unit the use of technology integration in a variety of different areas. Students will be using a variety of technology tools throughout this unit to enhance their learning. Graphing calculators will help us visualize concepts, explore relationships between variables, and verify solutions. Desmos and GeoGebra, which are web-based graphing calculators and interactive activities, will aid in the visualizing and understanding of these mathematical concepts. Desmos will be a great tool to visualize the area under the curve when we explore Lesson 1, and GeoGebra will be an awesome addition to noticings and wonderings as class starters before diving into the material for the day. Integrating technology into our learning process allows for a more interactive and engaging educational experience. With respect to active learning and collaboration, learning by doing is the best way to learn. Throughout this unit, students will be working on problems and activities that will challenge them to think critically and apply their knowledge. We'll be working in pairs, small groups, allowing students to learn from each other and develop their communication skills. This collaborative approach will foster a sense of community and shared responsibility. Engaging in active learning and collaboration not only enhances a student's understanding, but also prepares them for the real-world teamwork scenarios they will encounter. Speaking of real-life connections, one of the most exciting things about calculus is how applicable it is to the real world. In this unit, students will see how integrals are used in various fields, including physics, engineering, and economics, just to name a few. By the end of this unit, students will not only have a strong understanding of integrals, but also see how they can be used to solve these real-world problems. Making these connections helps students appreciate the practical significance of mathematical concepts and motivates them to learn much more. As far as assessment goes, you'll see a variety of different assessments throughout my lessons. There will be various assessments throughout the unit to gauge a student's understanding. These will include daily participation activities, exit tickets, class discussion, homework assignments, learning menus, and summative assessments. Don't worry, these assessments are designed to help students learn and improve, and there will be opportunities to ask questions and get clarification throughout the unit as we believe in a positive learning environment and a growth mindset. Regular assessments will help ensure that students are mastering the material and are able to have feedback for continuous improvement. To wrap up this unit, students will be working on a project where they'll get to choose a real-life application of integrals that interest them. Students will research the topic, solve a relevant problem using integrals as they showcase their learning by their choice of presentation. This is a great opportunity to showcase a student's creativity, problem-solving skills, and understanding of integrals. Project-based learning encourages deeper engagement within the material, allowing students to explore what interests them and apply their knowledge in a meaningful way. By structuring our lessons around these key areas as discussed above within all units, we aim to provide a comprehensive and engaging approach to learning about not only integrals, but calculus as a whole. Through a combination of theory, technology, active learning, and real-life applications, students will develop a strong understanding of how integrals are part of a well-rounded calculus class, which can be used to solve a wide range of problems.